Okay, I'm assuming you've already read this question, and let's just go ahead and dig into it. I'm going to remind you that the given information it actually does reference in this one exponential growth. So maybe you started with the differential equation, but you probably jumped right to, here's what I know. My equation is going to be of the form A equals CE to the KT power. Okay, so let's sort out our given information, or that's what I like to do. There are 100 flies after the second day of the experiment. So if I'm kind of listing out my time and my amount, my population, I've got 2 and 100. 300 flies after the fourth day. So after the, fourth day, population's up to 300. And approximately how many flies were there in the original population? Interesting. So we're actually asked two questions here. We're trying to figure out at time 0, what's my amount? And then how long until there are 10,000 flies? So again, just thinking about the algebra here, once I get my equation to have a C value and a K value, then I'm down to an equation with two variables, A and T, and I can plug in one, find the other, and vice versa. So my task becomes, let's solve for C and K. Very much like the last one, but it's going to end up a little bit different because I don't have my starting amount. So the fact that I don't have this coordinate is going to make things a little complicated. But we're going to start it the exact same way. So I'm just going to take one of my coordinates here. I'm going to take this first one that I listed out, and let's plug that in, and let's see what happens. I get 100 equals CE to the K times T is 2. Okay, or sometimes we like to write that like 2K, but that's the same thing. So if you recall the last one, we ended up with e to the 0k, which is just e to the 0, which becomes 1. This is e to the 2k, which isn't going to go away. So I have two variables. I can't solve an equation for two variables at the same time. So I'm thinking algebraically. I'm basically going to have to create a system of equations here. Good news is that I have extra information here, so I can use this. Let's just go ahead and use my same equation and plug in my second coordinate point there. So I've got 300 equals CE to the K times 4. And then let's just pause and look at that. So I've got two equations right there. And I need to solve for C and K. So why don't you actually pause the video and try this, see what you can do. Okay, I'm assuming that you tried it. There's a lot of different ways that this could end up looking. So I'm going to go ahead and show you what I did. I don't know that this is the easiest way to do it, but this is what worked for me. So I'm taking the equation on the left-hand side. So I'm going to divide by, take my 100. Oops, that's a little sloppy. Let's try that again. 100 and divide by e to the 2k. So I'm taking this entire term e to the 2k, dividing on both sides to get c equals 100 over e to the 2k. And then I'm going to take on this other equation and do the same thing. Take my 300 and divide by e to the 4k. So take that and divide by it, and that's equal to c. Because remember, c is the same thing in both problems. So I'm using substitution if you're thinking in terms of system of equations, and I now have c equals this and c equals this. Therefore, I know that those two quantities have to be equal to each other. So I'm going to take those 100 over e to the 2k and set that equal to 300 over e to the 4k. Essentially substituting one in for c. And let's hope that this is solvable. Oh, come on. Okay. Pardon with me on my screen. Let's go. I just need a little more room to work. And let's see what we can do with this algebraically. I guess I'll cross multiply on both sides because I'm not sure what else to do. So 300e to the 2k is equal to 100e to the 4k. I'm solving for k, and right now I have k on both sides, which I'm not crazy about. So I'm thinking a couple things. I'm thinking if I do a log, then that's going to get it out of the exponent. but I'm going to end up with it on both sides. So I'm going to first try to combine my k's if I can, and I'm remembering some properties of exponents that might help me here. So I'm going to divide by, I'm basically going to rearrange my proportion, and I maybe could have just done it straight from here. Maybe you saw to do this. I'm going a little bit the long route, I suppose, but I'm going to divide by e to the 2k to get rid of it here. And then I'm going to divide by at the, well, let's do it one step at a time. So 300 is going to be equal to 100 e to the 4k over e to the 2k, which I'm going to write as e to the 2k. So I'm taking this, I'm remembering my exponent property that I can write that as e to the 4k minus 2k. When I'm dividing two terms with the same base, I can subtract their exponents. So that's giving me my e to the 2k. And then I'm going to go ahead and divide by the 100 to isolate my exponent. And this is going to start to look better. So 3 equals e is equal to e to the 2k. I'm solving for k, which means, whoops, I'm going to take the natural log of both sides. Exponent comes out front. And I'm going to end up with natural log of 3 equals 2k times the natural log of e. Natural log of e is just 1, and then I'm going to divide by 2 on both sides. So my k ends up being natural log of 3 over t. Okay, so let's figure out what the heck we just did. Remember that, natural log of 3 over 2, because I'm going to have to move some stuff and find our initial problem here. Okay, so way back here in the beginning, we had this lovely basic form of an exponential equation. I've now gotten that to the point that I know a equals ce to the natural log of 3 over 2 times, whoops, not times k times t. Okay, so from here, we need to now solve for c. Just keep like big picture perspective here. I need to solve for c. That's my whole goal. Once I get c, then I have an equation that I can work with to plug in a time, get an amount, and plug in an amount and get a time. I'm going to let you take it from here. So we need to solve for c. As long as we have an a and a t in there, we can solve for c. That would be our unknown. We've got 2 points that we can use. So your pick, plug one of those in, solve for c, and then you should be able to answer the question. Follow what we did in the last one. You should be good with that one. Okay, quick help with this one. Go ahead and pause the video if you haven't already read through it, and try to make sense of it yourself. You've worked with this also. This is not a new concept, but there's going to be one thing that works out differently here that's might confuse you. So, rate of decay of radioactive substances is proportional to the initial amount of the substance. I just want to reinforce the calculus there. We've got the equation dAdt, the rate of decay of the substance, that's the rate of change of the amount with respect to time, is proportional to, that means k times the initial amount of the substance A. Okay, or the other way of thinking of that is if we were to divide by A on both sides, dAdt over A, the ratio of those two things is equal to some constant. Okay, we've already seen that's going to turn into my exponential equation. When I actually do the calculus, solve the differential equation, it's going to turn into my exponential equation A equals CE to the KT. Okay, but that's where I'm getting it from, is from this initial reading right here. Now to the actual question. So this problem doesn't actually give us as much information as the other ones, which might bug you a little bit or be a little concerning. So that's the part I wanted to help you with. Let's set this up the same sort of manner, figure out what information I have. Carbon-14 has a half-life of 5,700 years. So my time is in years this time, and I'm recognizing that at 5,700 years, something is happening. I've got half the amount of the substance that I started with. So here's the problem. I don't know how much I started with, but I know that whatever I started with, I'm going to have 1/2 of that. So we could use A, but A's already in the problem. So I'm just going to pick some other letter to represent the amount that I started with. And I used C. And the reason is that C in this problem C, you might have noticed, is the initial amount. Go back to the example that we did with the first example with the hornets, and you'll see that that ends up being my initial amount. So whatever that is, I'm going to have 1/2 of it after 5,700 years. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. So I want to find, the question's asking, find the time when, I guess I've been representing that as a question mark, when 10% has decayed. Well, this is the amount, right here I'm putting the amount that I have left. So instead of putting 0.1 for 10%, I need to say that I have 90% left. So I'm going to represent that as 0.9 times C, 0.9 C. So this question, I'm going to, it might be a little concerning because I don't have as much, I usually have 2 coordinate points here. I'm going to take this and plug it in over here and see what happens. So I'm going to have 1/2 C here equals CE to the K times time is my great big 5,700. Maybe you're seeing a little chemistry in this one. And let's go ahead and solve and see what happens. So first thing that I would do is divide by C, whatever that amount is, and the C's cancel out. So there is a special half-life formula, and maybe you remember it. You can certainly look in your textbook. It's not a secret that we have a half-life formula, but I'm not somebody that likes to memorize formulas if I don't have to, because I forget them. So I don't have to memorize a formula here because it just ends up giving me, but the half-life formula has to do with, we just start with that 1/2 because the C's will cancel out. From here, you should be able to solve for K. Take the natural log of both sides. Once you have K, you have a workable differential equation, or sorry, exponential equation that you can use. You're not going to find the C amount, but you're going to have the K value, and this is in terms of C. So once you put 0.9 C here, after you have the K, then the C's are going to cancel out again. Okay, just another variation of this. You could, if you wanted to, you could make up an initial amount, and then you could work the whole problem with that. So you could make up some amount for what this is going to be. I'd go with something easy. Let's say we have 10 grams or whatever. We could start with 10 there, and then this would be 5, and then this would be 9. And it would work out perfectly as long as those relationships are true that you have. So if you feel better working with numbers, that's fine. We should also be able to make sense of working with the variables. Hopefully that helps. You're going to have to do a little work to finish that one, but you should be good. Your answer is a very large number, just to give you a warning.